20-1, hello to you all. Here we are back again for another lesson. So it's interesting that we're going to take a little bit of a step back today. We started to solve for quadratic equations using the graphing process, figuring out what x is. There's three other methods that we're going to use. The next method uses factoring, grade 10, factoring polynomials. I know a majority of you absolutely loved it last year in 10C. You got to know it. So I'm going to do a bit of a long video. We're going to review what factoring is. And you're going to have a couple days to do the assignments I suggest. I'm not going to post for a couple days because this factoring, it needs to be done. We are going to use it this unit and our unit in the future, and it's going to be important. So real quick, what is factoring? Factoring is, well, turning polynomials, or for that matter, anything, into a multiplication question. So it could be something as simple as 24. If I want to factor 24, I want to create a multiplication question. Well, that means this could be 2 times 12. I factored it. It's now a multiplication question. It could be 6 times 4. It could be 3 times 8. It could be 3 times 4 times 2. All of these are factored forms of 24. Now, with that being said, it's not just about numbers. It could be polynomials. Well, if I take a polynomial term, 60 x cubed y to the 4, and I want to turn that into a multiplication question, well, all kinds of ways to break up a polynomial term because of the variables and whatnot and the numerics. Possibility could be 6xy times 10x squared y cubed. There's the factored form. If I were to multiply these two things, 6 times 10, there's our 60. x1 times x squared, there's our x cubed. y1 times y3, there's our y4. With this, all kinds of possibilities. 2 x squared y squared times 30 xy squared, another possibility. Tons of possible ways to factor terms. But what we're going to review is turning multi-term polynomials into multiplication questions. And this was all done last year. 4 basic factoring situations that we need to review and recognize. Greatest common factor factoring, simple trinomial factoring, complex trinomial factoring, and difference of squares factoring. Lots of information to get through. Be patient. Here we go. First type, greatest common factor factoring. We did already deal with this a little bit this unit, but not a ton. So officially, greatest common factor factoring. First thing is to identify a common factor. When we work with a common factor and we want to identify, it's the biggest amount that is common to all 3 terms in this case. So the common factor, we have to consider the coefficients, the numeric parts. So we want, with this case, 5, 20, and negative 15. What's the greatest factor that'll divide into all of those? Well, in this case, the coefficient would be a 5. Now, the second part to greatest common factor factoring is the variable components. And the variable components is the most of each variable that could be pulled, is how I refer to it, sort of pulled out of each term. This first term has an x squared, which is an x times an x. This second term has an x. This third term has no variables. We have 2 variables, 1 variable, and no variables. So in this case, there is not a variable term that could be factored out. We simply have the common factor, the greatest common factor for this is 5. And our greatest common factor is the first factor of the factored form. We're going to turn this trinomial into 5 times something. Well, the second step, how do I get the second factor? I divide the poly by the greatest common factor from step 1. So we need to divide this trinomial that we started with, now that we have a GCF, has to divide by the 5. Remember, all terms in a polynomial need to divide by what you're dividing. So 5x squared divided by 5 leaves us with 1x squared. 20x divided by 5 leaves us 20 divided by 5 is 4, and it's an x term. And then negative 15 divided by 5 leaves us with a negative 3. So the factored form would be x squared plus 4x minus 3 times the 5. There's your factored form using GCF factoring in this case. 2 ways to check, or 2 things to look for. First of all, are there common factors left in our division step? X squared, 4x, negative 3. There's no more common factors. So we did factor out the largest one. The second thing is we could always multiply to check. We don't want to multiply to end up with it. We just want to do a quick check. My check, if I distributed this 5, I would have 5x squared, 20x, and negative 15. 5x squared, 20x, negative 15. That's what we started with. So in my check, I know that my factored form is correct. Greatest common factor factoring. So let's try this one. 8x cubed minus 4x to the 4 plus 12x squared. This type of factoring this time, greatest common factor factoring. So here we go. What do we have in this case? First step, what's the GCF? Well, consider, first of all, your coefficients. 8, negative 4, and 12. GCF is going to have a 4 in it. What else? Well, I need to consider x cubed, x4, and x squared. Here we have 3 x's, here we have 4 x's, and here we have 2 x's. The most x's that could be removed from each of these would be 2 of them. So we can factor out an x squared as well. So there's the GCF. So I know that this trinomial can be factored into a form of 4x squared times something. What's my second step? I divide by the GCF. And when I divide by the GCF of 4x squared, I have to divide every term by it. Divide coefficients, subtract exponents. x3 divided by x squared, 3 minus 2 leaves us with an x1. Negative 4 divided by 4 is a negative 1. x4 divided by x squared is x to the 4 minus 2, or an x squared. 12 divided by 4 is 3. X squared divided by x squared leaves us with an x to the 0. We really don't need it. So our factored form, 4x squared times 2x minus x squared plus 3. There's, again, our factored form. We took our initial trinomial and we've split it into a factored form where we factored out as one of the factors the greatest factor for every term. So there's your GCF factoring. Now, second type, simple trinomial factoring. Well, a simple trinomial, first of all, it's a trinomial. What we want to look for is a situation like this. Trinomial, 3 terms. For it to be a simple trinomial, the x squared term that's first has that assumed coefficient of 1. There's nothing with the x squared other than a 1. That's what makes it a simple trinomial. You then have an x term and you have a constant. So in this situation, B and C essentially are integers, positive or negative whole numbers. If you have this type of trinomial, we have a trinomial that we can try simple trinomial factoring with. You need to learn to recognize it. So with that being said, what do? And again, we very briefly talked about this last unit when we were looking at completing the square, but it was a very unique situation. Again, simple trinomial, x squared, an x term, and a constant. We need to find two numbers, and the two numbers have to multiply to the c value, but they also have to add to the b value. So I need two numbers that do that. Multiply to 20, add to 12 in this case. Well, what are two possibilities? First of all, my suggestion, always work with the c value. There's fewer combinations to multiply to get 20. Think of those first. Let's just try 2 and 10. That's going to multiply to 20, but when I add those, I get 12. Well, look at that. There's my 20, there's my 12, there's my combination, and it simply becomes binomial x plus 2 times binomial x plus 10. A simple trinomial will always factor into x plus something times x plus something if it's a simple trinomial. There's your factored form. Factor 1 is x plus 2, factor 2 is x plus 10. Now, I always get students that look at that and think, well, binomial and a binomial, that's not going to give me what we started with. If you want to do a check, remember to FOIL. If I FOILed this as a check, x plus 2 times x plus 10, first, outer, inner, last. That would give x squared plus 10x plus 2x plus 20. Combine the like terms, x squared, 12x, and 20. This is the factored form for our simple trinomial. Two numbers, multiply to the constant, add to the coefficient on our x. When you find the combination, it's your factored form. So x squared minus 23x minus 24. First things first, x squared, x, and a constant. Make sure you have a simple trinomial. We have the simple trinomial. So what do we need? We need two numbers. Multiply to negative 24, but add to negative 23. We want to multiply to negative 24, add to negative 23. Well, start with the negative 24 as my suggestion, fewer combinations. What about 3 and negative 8? Multiplies to negative 24, but it adds to negative 5. Doesn't work. What else will give us negative 24? Well, you have a negative 2 and a positive 12. Multiplies to negative 24, adds to 10. Doesn't cut it. Sometimes the one that's a little goofy for these, still working with the negative 24, a lot of times we always talk about multiplying by 1 does nothing. But in this case, if I work with 24 and 1, and one of them has to be negative, let's try the negative 1. This will multiply to negative 24, and it adds to positive 23. We need a negative 23, so we got the right numbers. If I just switch my signs, negative 24 and 1 gives me a negative 24 when I multiply. Negative 24 and 1 gives me my negative 23. There's the combination I need. So the factored form would be x minus 24 times x plus 1. Trinomial has become a binomial times a binomial. If we did FOIL, we would end up with what we started, and that would be a good thing. There's your factored form. Simple trinomial. Now, with that being said, we have a few special cases of special trinomials, special simple trinomials. First thing, this particular question, it doesn't look like a simple trinomial. We don't have an x squared by itself. Well, there's two things to do. The first thing, though, is to understand, always look GCF factoring to start. Every question, every time you get asked to factor, you should start with a GCF. Is there a GCF in there? So we have negative 5x, 20x, and a 60. In fact, we have a GCF of 5. So I'm going to factor GCF of 5. What does that leave me with? Negative 1x squared, negative 4x plus 12. Now, whenever we do GCF, once that's done, look to see if what remains is factorable. Look to see if the remaining is factorable. So in this case, after we've taken out the GCF, well, x squared, x, and a constant. But in this case, the x squared isn't by itself because we have a negative out front. Well, I almost have what I need with the x squared, x, and a constant, but I don't want the negative. So sometimes, in this case, your GCF needs to be negative. If I factor out, if I go back up to my GCF and factor out a negative 5, well, let's see what happens. Because I had the right stuff, but the wrong sign. So if I change my GCF now to negative 5 and factor that out, I'm left with 1x squared, which is really just an x squared. That's what we need. We have a positive 4x and a negative 12. Now, after we did the GCF, is the remaining factorable? Now we have the x squared, the x term, and the constant. X squared is by itself, so sometimes your GCF is going to be a negative. At that point, now we can do simple trinomial factoring to finish off the question. So one special case is sometimes there's two-step factoring. So with that being said, what's going to multiply to give us negative 12, but add to give us 4? Well, the combination here, positive 6, negative 2, multiplies to negative 12, adds to 4. So we'll now have x plus 6 times x minus 2. Don't forget the negative 5 out front. And there's our factored form of our original trinomial. Didn't start off as a simple trinomial, but after the factoring, it became a simple trinomial. So GCF to start, simple trinomial afterwards to get a factored form. So watch for those. Next case is the x squared plus xy plus y squared. Well, this isn't a simple trinomial with the right stuff, but it kind of has the right stuff. We have an x squared, we have one x and no x's. So the trick is, if you have an x squared, a y squared, and one of each in the middle, or an a squared plus an ab plus a b squared, b squared, one of each in the middle. This is the special situation. Drop the y to start. Because if I just drop the y off, I'm going to be left with, by dropping the y's, well, now I just got rid of the y's for a second. Now I do have a trinomial with the right stuff. So I'm going to factor this. Multiply to 56, add to 15. I believe the combination is 8 and 7. So I'm left with x plus 8 and x plus 7. But notice I left a little bit of a gap here, because after we drop the y, we replace the y. The y needs to go back in, and we have just one y in for each. So, unique situation again, where you have this x squared, y squared, and one of each in the middle. You drop the second variable. Now you have your simple trinomial. You factor it, but don't forget to replace your y's afterwards. And again, there's our factored form. With that factored form, I could do FOIL, and we're going to end up with our x squared plus 15xy plus 56y squared from that factored form. So another special situation of simple trinomials. And now our last case for simple trinomials. Again, sometimes we have, and it's pretty much always going to be a binomial expression in the trinomial. But what's important, if you take a look, a plus 4 sort of happens in both. And these situations are just ones you need to learn to recognize. So it's an a plus 4 squared and an a plus 4 squared. Now, a lot of students will want to expand. Do a bunch of multiplying, do a bunch of combining of terms, and then get a trinomial or something to factor. This process, not good. It's not efficient. In this course, we're preparing for stuff where you need to be more effective. If you have the exact same thing, what we can do is we're going to just replace the a plus 4 with a variable. A plus 4 we'll just call x. So instead of a plus 4, let's say x squared plus, instead of a plus 4, we just have an x plus a 9. So we replace the a plus 4 with an x, and now we have the simple trinomial. We have something that can be factored. Multiply to 9, add to 6. What's your combination? Well, 3 and a 3. So this could be x plus 3 times x plus 3. There's the factored form for that simple trinomial. However, that's not finished, because we need to replace the x values now with a plus 4. Because we turned a plus 4 into x up here, well, now that we're factored, we need to replace x with a plus 4 again. So this becomes a plus 4 plus 3 times a plus 4 plus 3. We want to keep it in factored form. So our factored form here is a plus 7 times a plus 7. And there is what we're looking at as a factored form here. So there's the factored form for what we started with. special situation where we have the binomial expression within the trinomial. So all of these unique situations, you're not going to get an a plus 4 squared plus a c minus 2 or 7c minus 2 plus 9. You're not going to get it. It'll be a situation where they're the same expressions. That's what makes it work. So there's simple trinomials. In your booklet, page 14 has a section of a whole bunch of simple trinomial factoring. My suggestion, stop for a bit, the video, and go do a bunch of those questions. There's a ton. Walk through it, get the practice. That's important. And then when you want the next type of review factoring, come on back. So now we have complex trinomial factoring. Well, complex trinomial factoring isn't a lot different. We still have x squared, we still have a bx, and we still have a constant. But what makes it complex is we now have a value with our x squared. Again, it's a matter of recognizing. If you have a trinomial with something x squared, something x, and a constant, this is now complex trinomial factoring, which has a lot more steps to it. So let's walk through and review those. Here we go. Complex trinomial factoring. First thing is you multiply the a and the c value. That's what we want to start with. Multiply AC. 6 times 12 is 72. Well, the second step is simple trinomial process. The simple trinomial process, the only difference is we want to multiply to get the AC value. We still want to add to get the x coefficient. So that hasn't changed. After we multiply this AC, we need to find two numbers that are going to multiply to 72, but they also have to add to 17. Same kind of idea of what we just did with simple trinomials, but that initial first step of multiplying 6 times 12. So what two numbers will multiply to 72 and add to 17? Well, it's 8 and 9. So now that we have the combination, this whole process for complex trinomial is called decomposition. And this process is called that because at step 3, we decompose or split the x term. So I want to take what we had, 6x squared, but our 17x, we're now going to decompose it using the two numbers we just discovered. We now have an 8x plus 9x. Those are the two numbers we used. 17x is now 8x and 9x. Same value, but a different form. And we still have plus 12. So at this point, you now group the four terms in pairs. And after you group the four terms in pairs, you're going to GCF each pair. Lots of steps in this. So we're going to group our four terms into pairs. And I'm going to GCF each. So 6x squared and 8x. What's the GCF there? It's 2x. So I'm going to divide each term by 2x. That leaves me with a 3x plus 4. Because 6x squared divided by 2x is 3x. 8x divided by 2x is a 4. Now I GCF the second pair as well. Well, 9x and 12, I want to factor out a positive 3. So I'm going to divide each of those terms by 3. 9x divided by 3 becomes 3x. 12 divided by 3 becomes a 4. So there's the GCF of each pair. And the key is, what we got left with is the same thing. This 3x plus 4 is one of our factors. What's the other factor? The factors that got factored out. We now have 2x plus 3. 2x plus 3, there's the factored form of our original 6x squared plus 17x plus 12. Do the FOIL steps to check it. It'll work out. There's our 6x squared. There's 9x and 2x, or sorry, 9x and 8x. So 3x times 3 is 9x. 4 times 2x is 8x. 8x and 9x. There's our 17x. And there's our 12 on the end. So there's the factored form of a complex trinomial. Here we go again. Steps one more time. At this point, multiply a times c. Watch your signs with the negative. We have a negative 24. At this point, we want to do the same thing we did in simple trinomials. Multiply to negative 24, but add to negative 5. Multiply to negative 24, add to negative 5, negative 8 and 3. Multiplies to negative 24, adds to negative 5. So we're going to decompose the middle term. 2x squared. It's no longer a negative 5. It's now negative 8x plus 3x minus 12. If you had written these the other way, 2x squared plus 3x minus 8x, the steps will still work out as long as you do them correctly. Now that we've decomposed, we group and we GCF each. GCF here is going to be a 2x. So I factor out a 2x, leaves me with x minus 4. GCF here is going to be a 3. So that's going to leave me with x. Whoops. I forgot to write that I'm factoring out the 3. Don't forget that. Factoring out a 3, x minus 4. And from there, we have the common factor in each case of x minus 4. So that's my first factor. And 2x plus 3, there's my second factor. And there's the factored form for our original trinomial. Complex trinomial where we still have an x squared term, but something with it. With the x, with the constant. So at this point, page 15 of the booklet has some complex trinomial factoring, a bunch of it. I suggest you stop and practice. It's the only way to get good at this. Last type of factoring is difference of squares factoring. Difference tells us to subtract. Difference of squares. Well, difference of squares means that we need to have a term that's being squared and another term that's being squared. So that's what a difference of squares is. Again, it's a matter of recognizing a binomial being subtracted, and each terms are square rootable. Because I can square root x squared to get x. I can square root y squared to get y. So two terms being subtracted, each term is square rootable. Rootable. Don't know if it's a word, but I like it. So recognize it and you're good to go. Two terms, check. Being subtracted, check. Is each term square rootable? What do I multiply by itself to get x squared? Well, an x. What do I multiply by itself to get a 4? I don't worry about the negative right now. What do I multiply by itself to get 4? It's a 2. If I have binomial being subtracted, each term is square rootable. There's the two terms. We put an x and a 2 into each binomial with one of each sign, a positive and a negative. That's it for difference of squares factoring. It's that simple if you know to recognize it. Double check it. Let's do a check. And why does it work? X plus 2 times x minus 2, x times x, x squared. X times negative 2, negative 2x. 2 times x is a 2x. 2 times the negative 2 is a negative 4. The reason this works is because of the positive and negative, we end up with additive inverses. Positive and negative of the same thing, they cancel each other out. One of each sign will always give a negative second term. There's our x squared, subtract the 4. So there's the factored form. It's that simple if you recognize it. Two terms, check. Being subtracted, check. Both square rootable, check. X and a 2, x and a 2, one of each sign. It's that straightforward. So here we go. Can we square root 4x squared and 9? Square root of 4x squared, 2x. Because 2x times 2x is 4x squared. Square root of 9 is 3. There's our two terms. 2x plus 3 times 2x minus 3. There's our factored form. Or is it? Now I wonder, how many of you had 2x plus 3 times 2x minus 3 as your final answer? Because you're wrong. If we take a look at the original question, 4x squared plus 9, two terms, check. Being subtracted, no. This is not factorable anymore. Don't get caught. Totally wrong. Because we don't have a difference of squares. Always check that you have the right stuff. Oh, there it is. Two terms, both square rootable, being subtracted. This is where 2x plus 3 times 2x minus 3 will be the right answer. Because we have 4x squared minus 9 in this case, as opposed to 4x squared plus 9 last time. Always make sure you have the right stuff. 16x squared minus 25. Again, two terms being subtracted. Can we square root 16x squared? 4x. Can we square root 25? 5. Factored form, 4x minus 5 times 4x plus 5. Subtract and addition, which order they're in, doesn't matter. It's the same thing as 4x plus 5 times 4x minus 5. Either one's acceptable. Difference of squares. So difference of squares factoring, special case. If we take a look at this particular question, binomial, check. Being subtracted, check. Square rootable, no. But don't walk away from this question yet, because I talked about it earlier. GCF factoring always should happen first. Always, every question, look for GCF factoring first. 100x squared subtract 48y squared. Is there a GCF? Well, not with variables, but 148, common factor of 4. I can divide by 4 both of those terms. That'll leave me with 25x squared, and this one will leave me with 12y squared. And this is a lousy example. I did a terrible job of coming up with this example. Let's think of a different example. Well done, Macdonald. So let's just change this up a bit. Let's keep it 100x squared subtract, let's go 36y squared. Let's work with this one instead. Sorry about that, because we still have two terms. Yes. We still have subtraction. Yes. We don't have square rootable things, but we do have square rootable things. Again, yikes. Not a good example. Let's try one more time. 100x squared subtracts. Oh, off the top of my head, this is hurting now. Oh, I'm all embarrassed. What do I got? Let's go 16y squared. All right, here we go. So the GCF in this case, again, will be a 4. 4 will leave us with 25x squared subtract 4y squared. There's always still starting with GCF factoring first. Always. At that point, what's interesting is second step factoring. What do we have left now that we've factored out the 4? Well, we still have two terms being subtracted, and now we have stuff that's square rootable. So now we're going to have 5x minus 2y, 5x plus 2y, with that GCF that we factored out front. So difference of squares special case, always do GCF factoring first if possible. And then finally, last special case, x to the 4 minus 16. Two terms being subtracted. They're both square rootable. There's no GCF though. I have no coefficient that I can factor out, and I have no variables here that I can factor out. So I just have x4 minus 16. Square root of x4 is x squared. Square root of 16 is 4. So the factored form is x squared minus 4 times x squared plus 4. Why is this a special case? It seems like it's pretty straightforward. But what you have to be careful of is factorable remaining stuff. That's what you need to check. Is there factorable remaining stuff? Don't have a difference of squares because it's addition. But here I have two terms being subtracted, square rootable, x and a 2. So we still had a factor that got left that could be broken down to x minus 2, x plus 2. This factor, though, isn't factorable because it's a addition of squares. We just keep it as is. Always look to make sure what you have left is or isn't factorable. So special case, it's difference of squares twice. Sometimes you're going to get that. You have to watch for it. So lots of information. Difference of squares factoring. Booklet, page 14. Great section. But along with that, all factoring practice. Booklet, page 5. Whole bunch of random questions. All types. So all types of factoring are in there. You have to figure out which type to do. Also, some of them are going to be two-step factoring. Make sure after you've done GCF or difference of squares, do you have something that's still factorable? And then booklet page 16, here you have questions. You got questions there that all equal an equation. Forget the equation part to get a head start on what we're doing next. On page 16, just factor the left side of all the equations. I'm not going to do a lesson for a bit. I want you to take time, make sure that what you have going on with factoring is complete. It's going to be so important this unit and another unit coming up. Do all of this work, all factoring practice, complete. Take the time to do it because your life will be easier later on. Always a pleasure, ladies and gentlemen, talking to you. Take care.